So far we have solved the Schrödinger equation for one electron system, that is hydrogen atom, where we have considered a relative motion of uh, electron around the nucleus. But if we want to solve the Schrödinger equation for a multi-electronic system, let's say for helium atom or lithium atom, then there we have encountered a number of electrons are more than one. So the system becomes more complex, and eventually we cannot solve the Schrödinger equation exactly. We can solve this Schrödinger equation using some numerical programmings with the help of computer, but it's not always that a computer solution, that is numerical solution, will give you some physical intuition or physical significance of a state. And as a chemist, we are not interested about the exact solution, numerical solution of the system. We are mostly interested about the physical significance and the things which are required for some chemical change or chemical reactions and some chemical phenomena. For this purpose, we can solve this Schrödinger equation and by considering some approximation method. The available approximation methods for quantum chemistry, not only quantum chemistry, these are the approximation methods of quantum mechanics. Number one is perturbation method and number two is variation method. The perturbation method is not in the scope or present syllabus, so the scope or present study is the variation method. Variation method is an approximation method to solve the Schrödinger equation for a multi-electronic system like helium atom or lithium atom, and this type of method is extensively used in the computer programmings which are utilized to get the solution for multi-electron system. That I have already told you that the electron computer programming are used to find out the wave function and energy of a multi-electron system, that is the electronic structure. That type of computational calculation are called electronic structure calculation. For this purpose, variation method is extensively used. Now we have solved the Schrödinger equation for hydrogen atom. Think that two hydrogen atom, this hydrogen atom 1 and this hydrogen atom 2, are bringing closer together. Okay. Now if they form a bond, then the energy of the system will decrease, and if the energy of the system increases, then there will be no bond formation. We are well known about this from our very childhood study, and we can see that this is two hydrogen atom. When they are in an infinite distance, then their energy reduces, and it will be minimum at a point where they form the bond, where they form the bond and they form a H2 molecule. Further, if we try to push these two atoms, then they will reach the limit of their internuclear distance, and these two nuclear repulsion becomes very prominent, and then again they are braked, so there will be no bond formation. So this is the equilibrium bond distance. And in many chemical problems, we are not interested about the excited state, because one can study about the ground state, excited state by solving the Schrödinger equation exactly. That is, the exact solution of a Schrödinger equation can help us to find ground state energy, ground state wave function, as well as higher energy states of the system. But we are not interested, as a chemist, we are not interested in the higher energy excited state. So mostly all the chemical things are happening in ground state. That is, I am talking about the ground electronic state. I am not talking about the excited state which is not associated with the electronic structure alternation, or there is no change in the electronic structure. Okay, so we know that the Schrodinger equation, time independent Schrodinger equation for a system is H psi equal to E psi. E is the energy of the system and H is the Hamiltonian for the system. Now, if I consider a 2 electron system, which is typically a helium atom, where these 2 electrons are electron 1 and electron 2 are sitting in this place and that place, and they are circulating around a nucleus of charge Ze. Okay. Now the distance from nucleus to electron 1 is R1 and for electron 2 is R2, and the distance in between these two electrons, that is electron 1 and 2, is R12. Now if I write the Hamiltonian for this system, then what will becomes, that is minus h cross square by 2m. M is the mass of the electron, this particle, and eventually if you want to do this relative motion in a single way, then what will become, it will be mu. So forget about this one. Now we are considering only the h cross square by 2m minus h cross square by 2m del 1 square, that is the term Laplacian operator for first electron, which contains the three coordinates which contains the differential terms with three coordinates of electron 1. Similarly, second one, for second electron, h cross square by 2m del 2 square. Okay, these are the two kinetic energy terms for electron 1 and electron 2. This is for electron 2, this is for electron 1. Now the potential energy will be appearing due to the attractive force acting between nucleus and electron. As this is a stabilizing force, so that will be minus. So minus Ze square Ze into E by 4 pi, that is Ze square by 4 pi epsilon 0 R1 for first electron. Similarly, for second electron, this potential energy will be Z square by 4 pi epsilon 0 R2, that will be potential energy for electron 2. And in addition these two potential energy, there will be another potential energy which is a repulsive potential energy in between electron 1 and electron 2, that is charge of 2 electrons, multiplication of charge of 2 electrons square by 4 pi epsilon 0 R2 R12, that is the distance between two electrons. So this is the interelectronic repulsive potential energy for the interaction between electron 1 and 2. If we look at this Hamiltonian, and if we put this Hamiltonian in the equation 1, then what will becomes? The equation 1 will have 6 differential terms depending upon 6 different variables. x1 is not related to x2 and y2 is not related to y1 and so on. So these are 6 differential terms and 6 independent different variables are involving in the equation 1. So it is very difficult to solve the differential equation. If one can solve this differential equation, then he or she becomes very famous, and most of the people do not try to solve this, and rather they are follow different way to get the solution. Very few scientists in the world, they have solved this equation. Now the question is very clear, that then how could we get the ground state energy or energy of a system. Okay, that is the question we have to address. We know that H psi equal to E psi. If I left multiply with psi star, then this equation becomes psi star H psi equal to E psi star psi. Now if I integrate over space and d tau volume element, now this d tau volume element contains all the 6 terms dx1, dy1, dz1, dx2, dy2, dz2 like this. Then I can have a chance to get E equal to this integral by integration over psi star over space and psi star psi d tau. So this is the one way to get psi, but for this we have to know the value of psi. What is psi? Unless until I know psi, I cannot get the energy. So that is, so this equation 2 becomes useless for now. So what will be the solution for this case? We will discuss in later time.